and welcome to our today's lesson. We are still on forces. Now, last time we looked at scalars and vector quantities. And we left at a point where we tried to define a scalar, and we said that a scalar is actually a quantity that has magnitude, or what we call the size only. It has the size only. Now, for example, if you had a mass of 10 kgs. Now, the figure 10 kgs gives you the units and the size of your mass and nothing else. There is actually not much you can say about this figure apart from identifying the fact that the mass has a size of 10 kgs, 10, and the units are kgs. Now, I gave examples, and just to recap, I'll give time, mass, speed, density, volume, distance, and length. Those are some of the examples that we can be able to give of scalar quantities. We have time, mass, speed, density, volume, distance, and length. It is worth noting that each one of these quantities has different units, as we will learn in our next chapter. Now, how about a vector? What is a vector? And a vector is a quantity that has both magnitude and direction. A vector is a quantity that has both magnitude and direction. Now, when we come to the representation, it is represented using a number, a unit, and direction. Now, clearly you can see there is a distinct difference between a scalar and a vector quantity, in that for a vector we are given an idea on direction of whatever quantity we are discussing. Take, for example, this line here. This line here. Let us assume it is 3 centimeters in length. Now, clearly you can see the size is 3 centimeters. Now, the unit is the centimeter, and the direction is given by the arrow head, that the size is 3. The units are centimeters, and then the arrowhead should give us an idea of the direction in which this quantity is acting. Now, before we go to the diagrammatic representation of vectors, I want us to talk about a few examples that we can give. Examples of vector quantities. Examples of vector quantities, we have weight, we have velocity, momentum, displacement, force, just to mention but a few. We have weight, velocity, momentum, displacement, and force. Now, remember that our topic is force. Therefore, we can say that a force is a vector quantity, and thus should be represented using a number, a unit, and direction. That force is a vector quantity, and therefore, if you want to draw any diagram that will involve forces, you have to clearly show the number that is supposed to give us an idea on the size of your force, a unit, and direction of your force. Now, before we move on, I will want to point out that force is measured in newtons, and we symbolize it with capital N. It is measured in newtons, and the symbol is capital N. Now, look at this line. Let us assume it is 5 centimeters. And now that we want to give it, to use it to represent a force, let us say it has a size of 5 newtons. Now, 5 is the size, N, or the newtons, is the unit, and the arrowhead should give you the direction of action of the force. Now compare that to this one. Say 2 newtons in the same direction. Now we could say the size is 2, The units are the newtons, and the force acts in the same direction as our first one. Now look at this. Again, let us assume the size is 5 newtons. So you look at the length of this line. It is actually equal to the first one. Let us do some labeling. So now our force A is equal to force B in magnitude. But look at the direction of action of the two forces. The first force, labeled A, acts in the right direction, and the effect of force C should be felt in the opposite direction. For that reason, we cannot take force A to be equal to force C, because the two forces act in different directions, but acts in different directions. Now, what am I saying? I'm saying for two forces to be considered equal, they should or must be equal in magnitude and should act in the same direction. I'm saying that for two forces to be equal, they must or should be equal in magnitude or the size, and then the direction of action of the forces should also be the same. Now, let me show you some drawings of forces that should be considered equal. Now, these pairs are equal. For example, in part A, the first force is 4 newtons in magnitude and acting in the right direction. And the same case applies to the force 2, which is also 4 newtons and in the same direction. If you look at the second pair, the two forces are equal in magnitude, and again, they act in opposite direction. So we can take the forces in each pair to have equal forces. Now, part B I will show you forces which might be equal in magnitude, but the direction is different, and for that reason these forces are not equal. These forces are not equal because the direction is different. So for a vector quantity, make sure you represent it using a number, a unit, and direction. And for you to consider two vectors to be equal, let them have the same magnitude and act in the same direction. Now, having looked at different types of forces, now it is good to note that sometimes a body can be acted upon by different forces, and for a balance to be achieved, then we have to resolve the forces and make sure we understand how they interact. Therefore, I want us to go through a concept that I'm going to call free body diagrams. And a free body diagram shows all the forces acting on a body, their size, and how they interact. That it is a diagram that shows all the forces acting on a body, their size, all their sizes, and how they interact. Their sizes and how they interact. Let us try and explain this by way of example, and I'll give you an example one of a piece of wood resting on a flat surface. A piece of wood that is resting on a flat surface. Now, there are forces that will be acting on this piece of wood. Now, whether the balance of the piece of wood is going to be disturbed depends on the interaction of the forces that act on it. Take this line as the flat surface. Take the line to be a flat surface. Now, place your piece of wood there on the flat surface. Again, we said that the piece of wood is resting. That means all the forces acting on the piece of wood are balanced. Now, what are the forces that are acting on this piece of wood? Number one is what we call the gravitational force. The gravitational force. And number two is what we call the normal force. The gravitational force and the normal force. Now, it is good to note that gravitational force is attractive. Is attractive in nature, and therefore it will always pull bodies downwards. That gravitational is attractive in nature, and thus it will always pull bodies downwards, and we assume it's towards the center of the earth. How about normal force? Now, whenever a body is acted upon by a force, it exerts an equal but opposite force towards the body. It exerts an equal but opposite force towards the opposite direction. Equal, opposite force in of reaction. That the gravitational force acts on the body and pulls it downwards. Therefore, the body also exerts another force in an opposite direction that should counteract the effect of the gravitational force. Now that our piece of wood is balanced, it means the gravitational force that acts downwards, this is the gravitational, is counteracted by another force that acts in the opposite direction, which we are going to call the normal force. Again, note the size of the arrows and the direction of the forces. The size of the arrows may be equal, but the directions are different. Therefore, the effect of gravitational force is cancelled out by the effect of normal force. And now that the magnitudes are equal, the force, the net force acting on the body should be gravitational force subtract the normal force, which will give you 0 force. Now, when the effect of one force is cancelled out in totality by another force, we say that the forces are balanced. Now, the two forces balance each other. When their effect cancels out, we say that the two forces are balanced. No force is greater than the other one, only that the difference is the direction of action of the two forces, and thus the effect of each is cancelled out. Now, let us look at a second example. Try to come up with a diagram of an egg. Example 2 is an egg falling freely towards the ground. Towards the ground and from a nest. Now, take your egg to be somewhere there. Now, this time you have gravitational force. You have gravitational force. And the normal force in this case is what we call the air resistance. The air resistance. Now, how do the two forces compare? Now, we have been told that the egg is falling. It is actually falling, therefore, it is not at a standstill. It is actually moving. Now, it means one of the forces acting on the egg should be bigger than the other one for it to produce an effect on the egg. Again, look at the sizes of the arrows and the direction of action of our two forces. We have an air resistance which acts upwards. Then we have the gravitational force which is pulling the egg towards the center of the earth. But now, in this case, our gravitational force is bigger than the air resistance, resulting to a downward movement of the egg. Therefore, in this case, the forces are not balanced. So the net force, which is given by gravitational force minus air resistance, is not equal to 0. It's not equal to 0. Therefore, whatever force that will result when we get the difference between the two is what dictates the speed with which the egg is going to fall. Let's look at yet another example. C. And C will involve a rightward force acting, a rightward force acting on a box. On a box and causing a rightward acceleration. That we have a rightward force acting on a box and causing a rightward acceleration. Now, forces acting on this box will include, number one is the gravitational force. Number two is the normal force. Normal force. Number three is the applied force. And the last one is friction. The question reads, a rightward force acting on a box and causing a rightward acceleration, and we should ignore air resistance. Therefore, the first question that we should ask ourselves is which forces are acting on this box, and we enumerate them as gravitational force, the normal, the applied force, and friction. Now, let us draw our diagram now. Let us draw our diagram. Now take this line to represent a flat surface. Like that. Then we have our box on the flat surface. Now let us resolve the forces. Force number one is the gravitational force. Again, remember, it will always pull objects downwards. So gravitational force is there. Gravitational force. Now, it is equally counteracted by what we call the normal force. Then we have two extra forces, and remember the question tells us that the box is actually moving towards the right. Therefore, the applied force will be towards the right direction. That is the applied force. Then equally, we have friction in the opposite direction. Now, look at the arrows even before we go to the resolution of the net force. We said that the arrows should give you an idea on the size of the forces. Now, the first pair is that of gravitational and the normal forces. Then we have the second pair that one of applied force and the friction force. Now friction opposes the applied force. Friction opposes the applied force, and that is why we draw it pointing to the opposite direction. Let us now resolve the net force. Net force A will be gravitational force. This one you subtract the normal force. And the answer to this one is 0, because our gravitational and the normal are equal but opposite. Therefore, their effects cancels out. Therefore, the force that acts on the box and emanating from the difference between the two is actually 0. In other words, what we say, if we just let the normal and the gravitational forces to act on this box without the interaction of the others, we would have expected our box to remain balanced. Now, the second pair will involve the applied force, and this one we subtract the friction force. And from our diagram, it is clear that the applied force is bigger in magnitude as compared to friction. Therefore, the net force is not 0. The net force is not 0. Now, and it is this net force, the difference between the two, that is going to accelerate our box towards the right direction. That once you subtract the applied force minus the friction force, the resultant force, which is not 0, is the one that propels our box towards the right direction. But then gravitational force minus the normal force is 0. Remember, when we talk about the difference, we talk about the difference in magnitude and direction. Therefore, if they are equal in magnitude but opposite in direction, then they cancel each other. If they are opposite in directions but unequal in magnitude, the difference between the magnitude dictates the direction of motion of the body. I want us to look at another example, and it will involve, that is example D, a box moving towards the right direction at a constant speed. A box moving towards the right direction at a constant speed. No. Our previous example talked about a box accelerating towards the right direction, which means it is moving with an increasing speed. Now, in this case, we want the box to move. We want the box to move, all right, but it should move with a constant speed, a speed that is not changing. Now, ask ourselves, what forces act on the box? Forces acting on the box now, number one is the gravitational force. Number two, the normal force. Three is the applied and four is the friction. The friction force. Now, I want us to divide our question into two. And part A, I want us to work it out ignoring air resistance, ignoring air resistance. And number two, will be considering the effect of air resistance. Now, let us start with the first scenario, where we want to ignore the effect of air resistance. Therefore, if we ignore air resistance, the forces acting on the body will be gravitational. There will be the normal. We shall have the applied, and we shall have the friction force. Remember that our box is to move toward the right direction and with a constant speed. Now, let us try and come up with that diagram. Again, we have our flat surface. We draw our box. Then we resolve the forces. Here, we are ignoring air resistance. So therefore, the first one is gravitational. That is gravitational force, which is now cancelled out by the normal force. Again, we have applied. We have applied force, which should also be opposed by friction force. Now, look at the sizes of the forces. Gravitational and normal are equal but opposite. Again, applied and friction are equal but opposite. Therefore, the effect is cancelled out, and therefore the box can move towards either direction because the effects of the forces are cancelling out. We go to the net force. We see that gravitational force, if you subtract the normal, will give you 0. Again, if you take the applied force, you subtract friction force. What you get is again 0. Now, when we have 0 in any other direction apart from vertical, then the box can move in whatever direction because it will be actually disturbed in either direction. Any trigger will make it move in any direction. Now, let us consider air resistance. So here, consider air resistance. So in this case, we still want the applied force to cause constant speed towards the right direction, and towards the right we have some two forces opposing motion, that is air resistance. Air resistance should also act in the opposite direction. Now, what happens for there to be some propulsion in the other side? The two forces should either balance, or this one should be bigger than the effect of the two. Therefore, in this case, applied force should be greater than or equal to friction force and added to air resistance. Therefore, what will happen, you need to elongate on your diagram, elongate the size of the applied force to show clearly that it is either bigger or equal to the effect of the two added together. So it doesn't matter how many forces opposes one force in the opposite direction, only that now you need to consider them when you are resolving them. Make sure If the direction of motion should be towards the right, then the applied should be equated or even made larger than the effect of the two. Probably we can look at the last example before we move to something else. And this one will be example number 6, because number 4 had 2 parts. So let us call it F. Now, a ball moving towards the right, let us this time make it left with increasing velocity. A, ignore air resistance, and B, consider air resistance. Now, let us resolve the forces acting on the ball. In case A, we will have gravitational, we shall have the normal, applied, and friction. And in B, we shall also include the effect of air resistance. Now, let us come up with those drawings. Let us come up with those diagrams. We have our flat surface. Then we have the ball. The ball, part A, shall consider gravitational. Gravitational force cancelled out by the normal. Then we have an applied force that should cause motion on the left. Motion towards the left side means it should be applied in this direction. That is the applied force. And then on the other side, we have friction. Friction. The friction force. Again, our ball is supposed to accelerate towards the left side. Therefore, this force should be bigger than friction, which cancels out its effect, and the resultant force is now supposed to propel the ball towards the other direction. So therefore, let us look at net force. Number 1, gravitational force, subtract the normal force, and the resultant is actually 0. Then number 2 should be the applied force, subtract the friction force, which should give you a net which is not equal to 0, like that. Now, let us look at our second case where we want to take into consideration the effect of air resistance. Effect of air resistance. Air resistance is supposed to oppose motion of the ball. Therefore, it is in this direction. That is air resistance. So when you come to the net force, again, gravitational force, you subtract the normal, you get a balance there. That is a balance of forces. The net is 0. Again, you look at applied force. This time subtract friction plus air resistance, and should give you a result that is actually not 0, so that the ball can manage to move towards the left direction. Therefore, free body diagrams should indicate all the forces acting on a body and how they relate, how they cancel each other and their sizes. The direction is very important. The sizes should also be considered, and there goes your free body diagrams. Now, in the course of drawing our diagrams, we have been discussing friction, and you might ask yourself, what is this friction that we are talking about? Therefore, I will want us to discuss something about friction as a force. Friction as a force. And friction basically is a force that opposes motion between surfaces. It is actually a force that opposes motion between surfaces that are in contact. Note, I am going to lay some emphasis on surfaces that are in contact. What I mean is, friction cannot be experienced by bodies that are not in contact. Two bodies have to be in contact with each other, and there has to be some movement between the layers of those particular bodies for us to be able to claim that there is friction between the bodies. They have to come into contact, and there has to be some motion between the bodies for us to be able to claim that there is friction experienced. I have my duster here and my book. I bring them into contact, then I slide my duster, and the resistance to the motion of the duster is what we call friction. Now, in our next lesson, we are going to look at types of friction. Then we shall try and find out whether there is any way at all we can benefit from this friction. That's all for today. Thank you.